Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the theorems on finite field. Theorems on finite field. Now see here. Show that every finite extensions of a finite field is normal. Show that every finite extension of a finite field is normal. Solution: let E be finite extension of a finite field F. Therefore, degree of E over F is equal to n. Then E is also finite and E star, the multiplicative group of E is cyclic and generated by U such that U raised to n minus 1 is equal to 1. U raised to n minus 1 is equal to 1. Therefore, U is a root of x raised to n minus x belongs to f of x. U is a root of x raised to n minus x belongs to f of x. All other roots of x raised to n minus x belongs to f of x. All other roots of x raised to n minus 1 minus x belongs to f of x are 0 and power of u. Therefore, all roots of x raised to n minus x belongs to f of x are in E. Hence, E is splitting field of x raised to n minus x belongs to f of x. Therefore, E is normal extensions. Therefore, E is normal extension of F. E is normal extension of F. Now, see your example on theorem. Show that a finite field. Show that a finite field F of p raised to n elements. P raised to n elements has exactly one subfield with p raised to n elements for each divisor m of n. Solution: we know that a cyclic group of order n has a unique subgroup of order d for each divisor d of n. Let m be the divisor of n. Now consider the cyclic group f star is equal to f minus singleton 0 of order p raised to n minus 1. Since m divide n, p raised to n minus 1 is equal to p raised to m minus 1 into p raised to m into d minus 1 plus p raised to m into d minus 2 plus plus p raised to m plus 1. n is equal to md. Thus, p raised to m minus 1 divides p raised to n minus 1. Then there exists a unique subgroup H of f star of order p raised to m minus 1. So for all x belongs to h, x raised to p raised to n minus 1 is equal to 1. Hence, x raised to p raised to n is equal to x for all x belongs to h intersection h union singleton 0. Therefore, since the roots of x raised to p raised to n is equal to x, Form of field H union singleton 0 is a unique subfield of F of order p raised to m. Of order p raised to m. Now see an example, one more example. If f of x belongs to capital F of x is an irreducible polynomial over a finite field F, then all roots of f of x are distinct. Then all roots of f of x are distinct. Let solution now see here. Let f be a finite field with p raised to n element. By corollary, f of x has multiple roots if and only if f of x is equal to summation of ai x raised to p raised to I. Because ai belongs to p, ai raised to p raised to n is equal to ai, set bi is equal to ai raised to p raised to n minus 1. Thus, f of x has multiple roots if and only if f of x is equal to summation of bi x raised to I raised to p is equal to summation of bi x raised to I raised to p, which is contradiction. Hence, f of x is irreducible. Thus, f of x must have distinct roots. Thus, f of x must have distinct roots. Example, now see here one more example. If the multiplicative group f star of non-zero element of a field f is cyclic, then f is finite. Let f star is equal to singleton alpha, where alpha generates f star. If f star is finite, then f is finite. So assume that f star is infinite cyclic group. Case first, the characteristic of f is p greater than 0. In this case, f is equal to fp of alpha, where fp is a subfield 0, 1, 2, 3 dot dot p minus 1 of f. Therefore, 1 plus alpha is equal to 0, then alpha square is equal to 1, which is a contradiction because f star is infinite. If 1 plus alpha is not equal to 0, then 1 plus alpha belongs to f star. So 1 plus alpha is equal to alpha raised to r, where r is some positive integer. In this case, 1 plus alpha is equal to alpha raised to r. It's a polynomial over fp with alpha as its roots. Thus, alpha is algebraic over fp. So, fp of alpha, degree of fp of alpha over fp is equal to degree of the minimal polynomial of alpha over fp is equal to r psi. Then f is equal to fp of alpha has p raised to r elements, which is a contradiction. So either the characteristic of f is 0, so f star p must be finite. Case second, the characteristic of f is 0, hence here 0 is not equal to 1 belongs to f. So minus 1 is equal to alpha raised to r, where r is some positive integer. This implies that alpha raised to 2r is equal to 1. That is 0 of alpha is finite, which is contradiction. Hence f star must be finite, so f must be a finite field.